Hey everyone, welcome to the next video from Chapter 7. So this video and the next couple are going to be a little hard, a little more difficult. They're going to be theoretical videos. So we're going to talk a little bit more of the theory of first order systems just to get that out of the way. Then we can go in to figure out actually how to solve these things because we got to know like what do general solutions look like? What are we looking for when we try to find solutions? Because if we don't know that, we can't really go towards finding them. So we got to spend a little more time on theory, a couple more videos on that, and then we'll go into actually figuring out how we can start going about solving these problems. So we're going to talk about the theory of first order systems. The theorems we get should look fairly familiar to you because they're going to be fairly related to the ones we saw before for second order equations and for higher order equations as well. You'll see similar theorems. So we'll talk about the theory. We'll see how it relates to those ones we talked about before, and talk a little more about what solutions look like and how we can visualize them. So let's go ahead and jump into it. So the theory of first order systems. So we're going to talk about existence and uniqueness theorems first, which you can relate to 2.4, 2.8, and 3.2 in the book for the similar theorems we had for first order, linear, nonlinear, and then second order equations as well. So let's start by looking at the general first order system, which looks like this. So there's our general first order system, and we're going to have a result that looks fairly similar to what we had in the second order and linear case and first order case for nonlinear equations. So I'll go ahead and write the result up and then we'll talk about it. All right, so here's the idea, theorem 7.1.1. So as long as I have my functions f, which are my right-hand side equations in my system, and all of their partial derivatives in the x directions. So that's f1 in x1, x2, x3, up to xn, f2 in x1, x2, x3, up to xn, f3, f4, up to fn in all the directions as well. If all of those guys are continuous, this is the same statement as if f and f sub y are continuous in a region of space for our first order nonlinear equations containing some initial condition. So this here is our initial condition point. Then there exists some interval, t minus t naught less than h, where there exists a unique solution. So this interval thing is the same thing we saw for the nonlinear equations in section 2.4, where if we had a nonlinear equation, we could say the solution existed and was unique only on some interval. We didn't know how big, just some interval around t0. And that's the same exact statement we're getting here, is that the solution exists and is unique on some interval containing t0. Because we had a very general equation, so we had a nonlinear equation, the best we're going to do is that some interval there's a solution. Or this should be very similar to the theorem we saw in section 2.4 for our first order equations. Now we can also go on and talk about our linear system, which is something that looks like x prime equals a of t x plus g, where A is the matrix P11, P1n, Pn1, Pnn. These are all functions of t, and G is the vector of t's. And we want to know what we can say about this for a theory of the same sort, an existence and uniqueness theorem. So it turns out we do get something that looks nice, and it should look very similar to the theorems we had in section 3.2 and section 2.4 for linear first and second order ODEs. So I'll write up the theorem and then we'll talk about it real quick. All right, so here we get the same result we had from sections 2.4 and 3.2. So that if everything in A and G is continuous, so by everything I mean all the P11, P12, P1n, Pnn, Pn1, all those have to be continuous, and the G1, G2, Gn have to be continuous as well. If all of those guys are continuous, similar to if P and G are continuous in the case of the first order equations, then for any t naught, so any starting point, and any initial condition numbers, there exists a unique solution that meets the conditions, and the solution extends all the way from alpha to beta, where alpha to beta is the interval where everything's continuous. So for linear equations, I get existence all the way up to where I stop being continuous, whereas nonlinear, I get this little subinterval thing like we talked about before for sections 2.4 and 2.8. So the theory you have here is more or less the same as you had for nonlinear linear equations for the first order equations, but now we have first order systems. The theories are still the same. It takes a little more work to state them in the proper way because you have to know about matrices and vectors and stuff to talk about them. But the results are basically the same, that if it's nonlinear, there's a unique solution on some interval around t0. And if it's linear, there's a solution that exists and is unique everywhere up to where the functions become discontinuous. All right, now the last point to make before this video is done is about how we can visualize these solutions. So all these solutions can be visualized as parameterized curves. For instance, if I have a two variable system, so I only have an x1 of t and an x2 of t, I can think of these guys tracing out a curve in x1, x2 space as t goes on. And I could draw this, right? I could have, say, x1, x2, and this be my solution, x1 of t, x2 of t. To get an equation for that, you could solve out for t and see what happens, but you can think about these solutions as being parameterized curves. It works a lot better in 2 dimensions, you can actually draw that, but even in like 4 dimensions, you could think of this as just tracing out a curve in 4-dimensional space. Now, from what we had before, by the fact that we can meet initial conditions and they are unique, means again, these curves can't cross. We had this for first order equations, but now we also have it for first order systems, because first order means that all I need to specify is the value at a point. So if I have the value at a point, I get a unique solution through that, which means if two solution curves cross, they have a problem at that point, and you can't have uniqueness there. So solution curves can't cross, and this gives us a way to sort of sketch out what's going to happen to curves as time goes on. And we'll start using that in the next couple of sections when we start talking about how to actually solve these problems. We'll solve them and then sketch solutions as parameterized curves in the plane, and knowing that they can't cross will be very helpful to be able to determine what's going to happen to all the different solutions. All right, that's the last point I want to make for this video. There's a basic rundown of the theory for existence and uniqueness. In the next video, we're going to delve deeper into theory and talk more about sort of the ideas from section 3.2, where we went into how do we know we have all the solutions we could get? How do we know we can meet any initial condition if we get a certain number of solutions? So we'll talk about the idea of the Ronskins coming back, things like that. We'll talk about all that in the next video. But that's it for this one. So thanks a lot for watching, and I'll see you in the next one.